All right, welcome to part 2 of the statistics review. In this portion, I'm going to cover topics such as mean, median, mode, also briefly percentiles. Talk about some different measures of variation, so range, variance and standard deviation, as well as the coefficient of variation. And I'll also mention symmetry and skewness. So we've got measures of location, talking about the mean, median, the mode. Also percentiles and quartiles give us ideas about location. We'll talk about measures of variability, so again, range, standard deviation, and variance, as well as the coefficient of variation. And then I'll be talking about symmetry and skewness. So we have population parameters, and they describe the distribution of a particular random variable. Now, values resulting from the data are called sample statistics. So these are used as estimators for the population parameters. The population parameters are unknown. We wish we knew them, and for the purpose of trying to understand what they might be better, we collect the data and estimate them. Now, when we're referring to items such as these, so mean or standard deviation, we can mean either the population value or the sample value. So that can sometimes be confusing perhaps. The mean is a measure of central tendency. The sample mean is denoted with the X bar, and then the formula here for that is given. You're simply adding up all of the elements, those are the X sub i's, adding them all up, and then divide by n, the number of observations that you have. If this were for the population, all that would change is that instead of going from I to little n, you might have something like a large N. You would have every single potential value that you observe in the population being added up and divided by the total number in the population. But for the population, we would use the Greek letter mu to denote that value. Unlikely that we would have that value. That would mean that we had the entire population at our disposal for examination. An example here, just looking at schools and tuition. So we've got some schools here in Arizona, and we've got their tuition values for the 2018-2019 school year. All that we're doing to find the sample mean is adding up those values and then dividing by, in this case, 3, since there are 3 observations. All right, median. This is an alternate measure of central tendency. What we have here is the middle value in the data, and at least half the observations are equal to or greater than it, and at least half are equal to or less than it, this value that we're going to look at. Now, with this at least half and at least half is that if you consider our example with 3 schools, at least half of them means 2, right? But that's actually more than half, because half would be 1.5. But we can't have clearly half of an observation or half of a school in our previous example, so at least half. Now, the median is often preferred to the mean when the data contain extreme values. So here's an example with the schools and the tuition. The middle value of these 3, we have the highest is here, so this might be the high. We have the lowest value is here, and this one, 11,059, is the middle value that we have there. Now again, these can be useful if there are extreme values. Suppose you had a larger number of schools and tuitions, and you happen to have a very expensive school, but there was only one very expensive school. That might distort one's view about the typical or representative cost of going to school. So the median would not pick that up in this kind of example. The mode is the most frequently occurring value in the data set. So example, a company might be interested in the mode for the number of times in a month that account holders check their online account. So what's the most frequent value there? Percentiles are another measure of location. The pth percentile of a data set is a value such that at least p% of the items take on this value or less, and at least 100 minus p, so the complement there, percent of the items take on this value or more. So again, you'll notice here that there's this concept of at least p% and at least p%. You also notice here that it says it's a value. There can be more than one way of getting this value. In fact, there are multiple ways of finding percentiles empirically, and they don't always necessarily yield the same value. So it's a value that meets this definition. And again, it has this at least portion here, which again suggests that there could be ties, for example, or it could be a little more because you've, again, in our previous example with the median, you had at least two values, right? Because you couldn't have 1.5. And so these are just some little points with this concept to note, or things to understand about that definition. So an example of using this, a company might want to target customers that spend in the top 10% for a special promotion. Well, then the company would want to find the 90th percentile and use that as a cutoff for who gets the promotion. In a credit example, you might be looking at those customers, those account holders that have the worst credit, maybe the 5% at the bottom, let's say, and they might be targeted for some special treatment as well, credit counseling or other kinds of actions. Percentiles and quartiles are linked. So a quartile is a special kind of percentile. There are specific percentiles. So there are the first, second, and third quartiles denoted with Q1 for first quartile, Q2 for the second, and Q3 for the third quartile. And they correspond simply to percentiles, the 25th percentile for Q1, the 50th percentile for Q2, and the 75th percentile for Q3. And these are often used to summarize the data and their distribution. Now, the next concept here to go over is that of variability. And this is of interest in many occasions because we can consider an example where we have the average, let's say an average purchase of $9.57, and that tells us the location, but it doesn't tell us how the purchases are spread out. So do all customers spend exactly that same amount? Maybe there's just one product and they either buy or don't. So all purchases end up being for the same amount. Or do all customers spend within $1 of that? So a very tight range. Or do purchases range from less than $1, so very small purchases here, out to more than $100? We have a lot of variability, if you will. So we want to think about what would be a way, or what are some ways that we might be able to measure this variability to distinguish between these three cases. Everybody spends the same amount, everybody spends within a little bit of the same amount, or there's actually quite a bit of variability. How might we do that? So there are a few different ways that we can measure this. We'll go over some of them here. They include the range, which is the maximum minus the minimum. Something called the standard deviation, which is also tied to the variance. I'll show the definition because it'll involve a little bit more of a math formula here in a minute. And then we have the coefficient of variation, and that's the standard deviation, which again I still need to define, divided by the mean, and then that's going to be expressed as a percentage. So the range is the largest value minus the smallest value. Its beauty is that it's simple to calculate. You simply need to know how to subtract, and you've got it. But it's sensitive to extreme values. Again, thinking about the tuition case, if we had one university that charged an unusually high amount, the range would increase. And then if that university increased its tuition beyond its already unusually high amount, then the range would increase as well. And so it's very sensitive to extreme values. So for example, let's suppose we have the values here 5.8, 7, 9.1, 10.5, 13.3, and we want to find the range. We've already got these ordered here, so we're just going to look at the largest value here, 13.3, and the smallest value, that's the 5.8. We take the difference between 13.3 and 5.8, and we get a range of 7.5. So that's how we would find the range. Then I have a couple of other examples here. Suppose the minimum is 5, the maximum is 25. Simply take 25 minus 5 and get 20. Another example would be that the smallest value is 56 and the largest value is 97. Take the 97, subtract 56 to get 41. So again, the range very simple to compute, but sensitive to extreme values. So on to the standard deviation and the variance. From a technical standpoint, the standard deviation is the square root of the variance. So conceptually, you're calculating the variance first, and the standard deviation is its square root. However, we typically refer to the standard deviation as opposed to the variance. The standard deviation in many cases is easier to interpret and is more useful for discussion. So the standard deviation is in the same units as the data. So if the values are in dollars, then the standard deviation is also going to be in dollars. If the data are in feet or kilometers or meters, whatever the case may be, then the standard deviation is going to be in that same unit. So feet, kilometers, or meters. So it makes it easier to interpret. So a graph to give you an idea about the standard deviation and what we're looking at here is we can have different spreads in our data. So the image here is of a distribution, and there is what I hope you'll see as being a black line, and I'll highlight that here. That's this line here is black. There's also a blue line, which I'll then highlight now here. And those two lines show different distributions which have different standard deviations. So the black line has a smaller standard deviation and the blue line has a larger standard deviation. So you have some notion or concept here about what we're meaning, what I mean when I talk about the standard deviation. How that would appear graphically is what we're representing here. But the definition for standard deviation, or the mathematical formula that we're using, how we're calculating this, is shown here. We often use the Greek letter sigma, and then it's squared. That's going to be used to represent the population variance. And so what it's showing here is we take each observation, that's the x sub I, you subtract off the mean, mu, and then that has to be squared. Now, in squaring all of those values, we get positive numbers, and then they get added up. That's what the sigma out here in front means, the capital sigma. So what we have here is the squared deviation from the average, right? So each observation, how is it different from the mean? That's being squared, and we're taking them all together. So they're all being added up, and then we divide by how many there are. So slight difference in moving to the sample value. So if we go to the sample variance, all that changes here is now instead of having mu, we have x bar, our estimate for mu. We perform the same function though. We square the deviations, add them all up. But a slight change over here, instead of dividing by n, we divide by n minus 1. And that's for reasons that I won't go into in this presentation, but that is the standard way of calculating the sample standard deviation, or here actually variance, but to get the standard deviation, we simply take the square root of those values. So whether we're talking about the population or the sample. So we take the square root of the variance. Now, when we're looking at the standard deviation and the variance, what we're thinking about in some sense is this is the square root, so if we're talking about standard deviation, of the average of the squared distances from the average value. So how far away are things from the average? Well, on average, they're going to be, the distance will be 0. That's by definition. But if we square those distances, right, and then we're looking at kind of an average of that squared deviation is what we're getting here. So the larger the standard deviations mean greater variability. And this can be seen in the graph that I showed a minute ago. The next concept for variation is the coefficient of variation. And the definition for that, the coefficient of variation, is the standard deviation, so that's the S, divided by the sample mean, that's the x bar, and then it's going to be expressed in percentage terms, so we multiply it by 100. And this is used to show how large the standard deviation is relative to the mean. So we might think about two different variables, and they might be measured very differently, and so one might have a seemingly large standard deviation, and another could have a seemingly small standard deviation. But we're looking at them here relative to the mean, so kind of fleshing out that element. All right, so an example with the coefficient of variation here, we've got again a repeat of the formula, but let's suppose we have average spending on meals and it's $27.51 and a standard deviation of 26.52. We're just going to take those values and plug them into the formula and get out 96.3% as the coefficient of variation. Now, let's contrast that though. Let's suppose that we were to use the same expenses, but they're measured in pesos. And let's suppose it's 20 pesos to the dollar. Well, in this case, the mean is going to be much larger, right? The average meal costs 550.2 pesos. Right? So if we're thinking about, again, we're supposing these are meals, but it's just any example you like. And the standard deviation is 530.4 pesos. So based on what I've said before, you have a much larger standard deviation. Does this mean greater variability? That's what one of the comments was just going back a minute or so ago. Does this suggest greater variability? Well, the coefficient of variation, we get the 530.4 over the 550.2. We measure that out. We get the same coefficient of variation. So this measure here is, because it's being taken relative to the price or the mean, which in this case is a price or an amount spent. But when we take it relative to the mean, then we're accounting for that, and it doesn't look perhaps as confusing, right, that 530 is a much larger value than 2652, but that's just an artifact that we're dealing with a variable that takes on much larger values, right? 550 on average as opposed to 27.5, because in this example it's being measured in pesos as opposed to dollars. That was the situation there. All right, last concept to cover here in this part is symmetry and skewness. So a symmetric distribution is going to look the same to the left and to the right of the median. So the proportion of observations that are within X, you pick a number, within X below the median will be the same as the proportion of observations within X above the median. Not all distributions are symmetric. The normal distribution is, so if you are familiar with the normal distribution already, that is a symmetric distribution, but distributions do not have to be symmetric. They can be left skewed, they can be right skewed. And examples of left and right skewed distributions are here, just an image how they would appear. Right? Left skew is that if you were to start at the peak, so here, and you were to ski down, you would be, or skateboard down, you would be going down to the left. Right skew, you start at the top of the mountain, as it were, and if you were to go down it, which side would you go down? You'd be skateboarding or skiing down the right side. That might be an easy way, hopefully, to help remember which is left skew and which is right skew.